Choosing this is going to probably be the most difficult because part of torque is the moment arm. It's how far it is away from something is from the axis of rotation. And since that is x, that distance there is x. If we choose this as our axis, then we're going to have x showing up quite a bit. All right, so let's take the first one mentioned, the one down at the bottom of the ladder. Technically, I'm just adding all the torques. It was in my hand too long, then I put it down here. There we go. So I have the torque from YH plus the torque from, I'll put WP plus the torque from the weight of the ladder plus the torque from the friction plus the torque from YV is equal to 0. I know those are already 0. Now, when we dealt with the beam problem on Monday, the moment arm and the force were perpendicular to each other. It was relatively simple. We don't have that here. For weight of the ladder, my moment arm is a vector pointing in that direction. I know that the magnitude of the torque is just going to be the magnitude of the force times the magnitude of the radial vector times the sine of the angle between them when they are tail to tail. Well, I know this is going to be half the length, so this is 10 meters. My force is the weight of the person, and let's put it on Earth 2. So the mass of the ladder was 10 kilograms, so the force would be 100 newtons. And the angle. Well, I know this angle here is 50 degrees, that's given in the problem. My force, my radial vector is pointing up at a 50-degree angle. My weight is acting down. So the angle here is that angle. 140 degrees. So my magnitude for the weight of the ladder, so this one is going to be 100 times 10 times the sine of 140 degrees. Well, what I haven't established yet, or we haven't established, is the sign. Is it positive or negative torque? Well, if we do R cross F, which way does your thumb point? All right, so
Towards the
move one into the board. You're agreeing with him? You don't seem sure.
I am.
You are, okay.
Well, where did the 110 come from? Oh,
That's, where did those come from?
yeah.
The moment arm
Mm-hmm.
is a vector from the axis to where the force is applied. The axis is here, the force is applied halfway up the ladder,
Oh, okay.
and it's a 20-meter ladder. The 100 is the weight of the ladder because it's 10 kilograms, and I put it on Earth 2, so G is 10 meters per second squared.
Got it.
All right, so one way of looking at it is R is pointing that way, F is pointing down, so like I would rotate my hand like that, thumb points into the board. Another way of looking at it is I picture a ladder. If I pick that as my axis of rotation, that is trying to rotate it around clockwise. Clockwise points my thumb into the board, and I said out of the board was positive. So this is negative torque. The weight of the person, we're going to go through a very similar exercise, it is in the same orientation as the weight of the ladder, and so therefore, it's going to be 600 times x, because that's the distance of the ladder it is, times the sine of 140 degrees. It will also be negative because it is also trying to rotate it clockwise. And now we're left with y sub h. R is a vector going from the bottom to the top. That's R, that's my force. I know that is 50 degrees. That is the angle that we're taking the sine of. That's 130 degrees. And so we have y sub h times 20 times the sine of 130 degrees.
What does it say after the x? Negative 60 with x.
That's sine of 140 degrees.
Sine 140.
I have two unknowns in my equation here, one of which is x, which is what I'm trying to find. I can solve for y sub v here. Once I have y sub v, I can solve for f. Once I have f, I have y sub h, so I can plug that in there and find the remaining. So, in terms of solving, y sub v is the weight of the ladder plus the weight of the person, which is 100 plus 600. Friction equals y sub h. Friction also equals, since I'm right at that breaking point, is y sub s times yv. Sorry, u sub s times yv, which is, I think I said 0.3, no, 0.4. 0.4 times 700, which is 280. So this is 280 newtons. And now we solve for x. Whatever that is. So x is going to be 1,000 times the sine of 140 degrees. Minus 5,600 times the sine of 130 degrees divided by 280, 2,800, 28 times 2 is 56, okay. Divided by 600, negative 600 times the sine of 140 degrees. Unless I made a careless error. And the final answer is, what's positive number? So I'm good on that. Everyone else got the same thing? Yeah. All right, units? Did anyone get something different? All right. Units? So this tells me, or tells us, I hope, that just before he gets to the halfway point, that ladder's gonna slip. Now suppose we go through all this, we got an x equal to 30 meters. What would that mean?
It's not gonna slip.
And if we had an x of -5 meters,
It's already slipping.
yeah, before he even steps on it. And you should get the same answer no matter what point you pick as your axis of rotation. The famed ladder problem. Now, in the classic ladder problem, on the wall is frictionless. If the wall has friction, we run into an issue with the fact that if it's not slipping, we don't know how much is, we don't know which one is at its maximum. I found one published paper where somebody actually did solve it, where I think they assumed that the coefficient of frictions were the same. They solved it, and then they actually experimented to see how close they got. I've gotten partway through the article, but I've not finished it yet. So you will not be subjected to that. I have covered chapters 9 and 10 at this point. Oh, nope, I've done almost all of it. I would recommend that you, if you've already finished master sets, wrong one. If you've already finished master sets 7 or 8, that you start working on 9 and 10. I still need to do conservation of angular momentum. And the classic shooting putty at a dangling rod. And other such nice things.
Anything about ladder, he's not supposed to stand on the top rung. They're charging for an extra thing.
I hadn't thought about it like that, but you know, it's what happens when a big ladder starts interfering with our lives.